Okay, so we're going to be talking about how we can use a secant line to help us with a tangent line. So the first thing that we need to do is we need to think about this as an equation and as a graph. So if I have some sort of function here, like so, this is going to be our function f of x. So, and I'm not even going to name it f of x, we're just going to call it f. So what we're going to be doing is we're going to look at 2 points. We want these points as generic as possible. So we are going to use the most generic things that we can possibly use, which is x, and things on how to describe the relationship between x and our other point. So I'm going to pick some value over here. This is x, which means if I were to follow this x value here, and then follow it over right here, this y value would be f of x. Okay, so one of our points is going to be x, f of x. So now, if I have a point so far away from x, or I have a point that is h away from x, we could call that point, or that x value, x plus h. So I just need some distance between our x value, and it can be whatever size, which is why we're using this variable h. So if I were to do the same thing, use this x value to find my y value, and we go over, this is going to be f of x plus h. So right now I have 2 points, f of x, and x plus h, f of x plus h. Okay, so what we're going to do is we are going to find the slope between these 2 points. So we're going to find the slope of our secant line. And I can call it a secant line because I'm just using 2 points here to make a line that passes through both of them. So we are going to do f of x plus h because in our graph that is the one that's bigger, so we're going to start with that one. So we have f of x plus h minus f of x divided by x plus h minus x. Okay, well, the top of this function, without knowing what it is, there's not a lot that we can do here. F of x plus h is kind of just what it is. F of x is kind of also just what it is. But in the denominator here, we can kind of simplify what we can. So we have f of x plus h minus f of x all divided by. We have an x, we're taking it away, so everything goes away, and we have h. This is actually something really specific. This is what we call the difference quotient. Difference meaning subtraction, quotient meaning division. So what this leads us to is what we call the limit definition of a derivative. So we're going to talk a lot this unit about derivatives because that's kind of the big idea of this chapter, and in fact it's kind of the big idea of the next couple chapters. So we're going to be talking about this thing called a derivative, and because we've been working with limits, we can use what's called the limit definition of a derivative to kind of help us out. So what we need to know about derivatives right now is that derivatives tell us slope. So we want h to be, sorry about that, we want h to be as small as possible, so we have h approach 0. So in order to do that, what we're trying to do is we are trying to close this gap. closer and closer and closer to that x value as we possibly can. So if I could get my x value here, that's going to give me a better approximation of our slope than here is. And if I can get it even smaller and smaller and smaller, all we're doing is making a better approximation. Well, the thing that we can use for that is a limit. So what we're going to be looking at is the limit as h approaches 0. The reason why h needs to approach 0 is because we are closing that gap. We want it as small as possible. And the thing that we're going to be taking the limit of is that difference quotient, f of x plus h minus f of x all divided by h, because this is our slope formula. So things that we need to know: if our limit exists, we have a slope. And even better, if it exists, we have a slope, and our slope is whatever our limit says. So that being said, there are times when our limit doesn't exist. So if the limit still doesn't exist after we've tried out our something else, then we just don't have a slope at that point. And that can happen in some different ways. So two of the biggest ways is when we have a function that is not continuous. So for instance, if I have a jump discontinuity, say here, right here at this x value, we're going to call it 2. We do not have a slope because there are two separate lines to look at. Because our lines are not connected, we can't find a slope at a singular point because there's more than one point. On the other hand, keeping with our continuity idea, if I have a function, say, something that looks like this, then we know that we have a vertical asymptote right here. And we're going to call this 2 again. It's hard to find slope when one's going upwards and the other side's going downwards, and we don't actually have a defined point at that spot. There is one more type of function, and that happens when our graph is continuous still. So the only other time when we don't have a derivative is when we have a graph that does something like this. This right here has a special name, and that name is a cusp or a corner, but a lot of the times they call it a cusp. So a cusp is a sudden change in direction. We can't find the slope at that point because if I had a function or a line here, this line could be going here, but I could also have it be at 0, and I could have it be going downwards. We just have a lot of possibilities for this line, and because we can't decide on a singular unique slope, we just don't have one there. So the other thing that we're going to talk about is just this last little bit, which is more of a vocab thing. We have a special word that you guys saw on that review, which is the word differentiability or differentiable. I have to look at how to spell it. So differentiability means we can take the derivative of a function. That's all it means, is that we can take a derivative of that function. So if we look at what we have here, there are going to be some cases where we can take the derivative, but maybe not at that singular point. So functions like functions like this, I can take the derivative of, but the derivative at a singular point isn't going to work. Functions like this one, though, and this one are piecewise functions. They cause some issues, or they cause a cusp, which means we can't take the derivative overall. So functions like absolute values, we don't have a way to take a derivative of it without having to like really, really dissect it. So the other thing that we need to talk about is that differentiability implies continuity. So if we can say something is differentiable, then we can automatically say that it is continuous. Okay, now going and thinking back to that example of a cusp, just because something is continuous doesn't mean it's differentiable. So differentiability implies continuity, but it does not work the other way around. So continuity does not imply differentiability. I can't take the derivative at our point here, even though it is continuous, because our limit and our y value are equal. So hopefully these notes were not too bad. Sorry if you got a jump scare from me accidentally hitting my pen to the mic. I will see you guys next class.